Hey everyone. In this video I'm going to review some basic concepts in calculus. And this is one of the most important aspects in our math review that we will need throughout the semester and beyond because ultimately calculus is a fundamental aspect of almost any statistical exercise. So even if we won't be computing derivatives or integrals by hand as we go forward, a lot of the concepts that we're using in, for example, maximum likelihood, or if we want to describe the expectation of probability distribution, or when we're talking about cumulative density functions in probability theory, ultimately all these concepts rely fundamentally on calculus. So let's jump right into it. First I want to talk about derivatives. So the derivative of a function f at x describes the rate of change at x. So in other words, how much does f of x change with a given change in x, in the input variable. So this rate of change is of course a fraction, so it's how much does f of x change for any given change in x. But this doesn't necessarily have to be constant over the range of x, right? Since not all lines are straight lines, they might rise more over a certain period or fall at a certain period. There are different values in the rate of change across different ranges of x, right? And so the derivative describes how the rate of change behaves for any given point in x, okay? In order to derive this, or in order to define the derivative, ultimately we'll need a concept that I discussed in the previous video, which is the limit. Specifically, a derivative is defined as follows. Let f be a function whose domain includes an open interval containing the point x. So it is defined, the function itself is defined at point x and is defined for an open interval around that point x, okay? Then the derivative of f at this point x is given by this limit. And we denote this here as d dx, the derivative with respect to x of our function f of x. And this is defined as a limit of f of x plus h. So f of x is the function value at point x plus h, so plus some kind of additional step that we take, minus f of x. So this is basically just the rate of change, how much f of x changes as we increase the input from x to x plus h, okay? And this is divided by x plus h minus x. So this is divided by essentially the change in the input. So from x plus h to x, and of course that cancels to h, right? So this is a basic fraction of how much do I change the input and how much does the output of the function, so f of x, change for that given change in the input. That's just one way of kind of expressing this basic fraction. Now the point is, we want to examine the instantaneous change for a very small change in x, right? And in order to characterize this, we ultimately evaluate this fraction, or we evaluate the limit of this fraction where h approaches 0, okay? And if this limit is defined, then f of x is said to be differentiable, okay? There are two main ways to denote this derivative that we'll see in textbooks. One is the Leibniz notation, which I already introduced here. So d dx is the derivative of f of x with respect to x. Or the prime or Lagrange notation, which is just f prime of x as the derivative of f of x, okay? And as I mentioned, if f prime of x, so the derivative of f of x exists at some point x0, then f is said to be differentiable at that point x0. And that also implies that f of x is continuous at x0. So here are just two basic examples. If you want to go through some some additional kind of practice examples, I would recommend just checking out again the Math Prefresher document, where you have some exercises and some solutions right available. So here are two different functions. In the upper left, we have f of x equals 2x. So that's a linear function, and that basically describes the straight line where with every increase in x, in every 1 unit increase in x, increases f of x by 2, right? So if I increase x from 0 to 1, then f of x increases from 0 to 2. And this is constant across across the entire range of x, right? And so if we look at the derivative of f of x, so f prime of x, we'll move here to the right, and we'll see that this is now basically a straight line where the derivative of f of x is equal, or so f prime of x is equal to 2 for any given value of x. Okay, so basically the straight line, the linear function f of x, has a constant as a derivative. If you have a slightly more complicated function like x cubed, here we have plotted x cubed from around minus 2.5 to 2.5. That's the usual shape of that function. We'll call this function g of x. And so if we describe the rate of change in that function, we know that this function is continuously increasing up to this saddle point where x is equal to 0, where x is equal to 0, this the slope of that function is actually 0. Okay, and so if we look at the derivative g prime of x of that function, we see that the slope itself, so the rate of change, is always positive. It's always above 0. It is higher as we move further away from x towards minus infinity or plus infinity, and it decreases up to this point 0, where it just touches 0. So at this specific point, this is a saddle point, and then it goes up to plus infinity, right? So you can see kind of the relationship between the shape of the function and how the rate of change evolves over the range of x in the way the derivative kind of evolves over the range of x as well. So there are a couple of properties, important properties of derivatives. So first, for the setup, suppose that f and g are differentiable at x, so two different functions that are differentiable at x, and that alpha is some constant, some unknown constant. Then the functions f plus or minus g, so the addition of those two functions, or alpha times f, or f times g, so the product of both functions, or f divided by g, are all also differentiable, right? So if we have two separate functions, so to speak, that are differentiable at point x, then we know that kind of a function combining, or the combination of those two functions, is also differentiable at point x. There are a couple of additional rules given this setup. First, the constant rule. So if we have a constant k that is multiplied by f of x, and we take the derivative of that product, then the derivative is just equal to k times f prime of x. So we can just take the derivative of f of x. We have the sum rule. So f of x plus or minus g of x. So now we have these two functions and the sum of these two functions, and we take the derivative. Then the derivative of the sum of those two functions is equal to the sum of those two derivatives. We have the product rule. It gets a little bit more complicated as soon as we have a product of two functions. If we take the derivative of f of x times g of x, then we have two parts of a sum. The first part is the derivative of the first function f of x, so f prime of x times g of x, the original g of x function. And then we add to that f of x times the derivative of g of x, so g prime of x. That's the product rule. We also have the quotient rule. So if we have two functions, f of x divided by g of x, and we take the derivative of that, then we have ultimately two parts. In the numerator, we have something that is looks very similar to the product rule, but we have to be a little bit more careful as to which function f of x or g of x was in the numerator or in the denominator, since here we subtract these two products from each other. So for f of x divided by g of x, if we take the derivative in the numerator, the equation is, or the derivative is given by f prime of x times g of x, now minus f of x times g prime of x, okay? And in the denominator we have gx, the original function, squared, okay? And this holds for, of course, only for g of x being not equal, or only at points where g of x is not equal to 0, because otherwise we would be dividing by 0. The power rule is kind of one of the most central rules when we work with polynomials, and it's basically just if we have a function of the form x to the power of k and we take the derivative of that, then the derivative is k times x to the power of k minus 1, and we see that basically the degree of the polynomial decreases by 1 with every derivative we take. We've already seen that kind of in the previous slide where I showed you, for example, for x cubed, how the derivative was x square, or 3x square, ultimately. Then we have the chain rule. So if we have nested functions, so for example, we take the derivative of f of g of x, then we have to take the derivative first of the outside function. So we take f prime of g of x, and we kind of leave g of x as it is, and then multiply this by the derivative of the inner function, so g prime of x. And then we have the generalized power rule. So if we have g of x to the power of p, not just x to the power of k, here we kind of have to both use the power rule and the chain rule. So we have on the one hand kind of the derivative of the outside function, which is p times g of x to the power of p minus 1. This is kind of just applying the power rule to the outside function, and then multiply this by g prime of x. And kind of constellations where you have something like g of x to the power of p is quite common, so we kind of want to keep that in mind as well. We can also, of course, not only stop with the first derivative, we can also take higher order derivatives. As we said, the first derivative sorry, we can basically just apply the same rules and the same arguments that we applied for first derivatives to the first derivative, or to the first derivative itself. And so we can kind of try to, with that, we can ultimately characterize the change in the rate of change in the first derivative, okay? So as we said, the first derivative is applying the definition of derivatives on the function, and it can be expressed as f prime of x. Sometimes we also see y prime, or dx of f of x, or dy dx. And we can, as I mentioned, we can keep applying the differentiation process of functions that are themselves derivatives. And in that case, the derivative of f prime of x with respect to x would then be f2 prime of x. And this is just exactly the same definition that we saw before. And we can call this the second derivative, or f prime of x, or d squared dx squared, in terms of notation. So similarly, the derivative of f2 prime of x would be called, or this should be, sorry, this should be 3. Oh yeah, the derivative of f2 prime of x would be called the third derivative and is denoted as f3 prime of x. And by extension, we can do this, basically n number of times. So the nth derivative is expressed as d to the power of n divided by dx to the power of n f of x. So for example, if we start with the function f of x equals x cubed, which we had earlier, the first derivative of that function is 3x squared. If we take the derivative again, we use the power rule again, and we're ending up with 6x. If we take the derivative again, we end up with the constant 6. And then afterwards, every further derivative is ultimately 0. But of course, not every derivative, polynomials usually or simple polynomials kind of reduce in degree, and ultimately you end up at 0, but that doesn't have to be the case for every function. Two types of derivatives that we encounter many times are derivatives that involve either natural logs or the exponent, or the natural exponent. So the functions e to the power of x and the natural logarithm, so log x, are continuous and differentiable in their domains, and the first derivative is for e of x, the first derivative of e of x is equal to e of x. So the rate of change is equal to the original function, which is why e, or e to the power of x, is so unique and so useful in many applications. And the derivative of log of x is equal to 1 divided by x. Oftentimes, of course, the functions that we deal with have some additional functions, have additional components, so we're not just dealing with e of x, but dealing with some composite function like e to the power of g of x, and if we want to take the derivative of that function, we have to use the power rule again, and so the derivative of e to the power of g of x is e to the power of g of x times g prime of x. Okay. Similarly with the log, if we have log of g of x and we take the derivative of that function, that is equal to g prime of x divided by g of x. Oops. Yeah. All right, so as I mentioned, the derivative of e of x is itself, so the rate of change of e of x is equal to the original function value, and so it describes an upward slope where the slope, or the rate of change at any given point, is given by the function itself. This also holds if there is a constant in front, since we can kind of use the constant rule. The derivative of alpha e to the power of x is equal to alpha e to the power of x. Of course, this holds for any order of derivatives. So even if we take the nth derivative, that relationship stays the same. As I mentioned, the chain rule, when the exponent is a function of x, remember to take the derivative of that function and add it to the product. So this is just what I mentioned earlier, e to the power of g of x times g prime of x. Okay. When it comes to the derivative of the log, wait a second. I'm sorry, the slides. Okay, sorry. when it comes to derivatives of the log, I have some issues with the math compilation, but that's fine. So if you take the derivative of log of x, that is equal to 1 over x. So d dx log x is equal to 1 over x. We had that in the previous slides as well. And as soon as we have exponents, so if we have d dx log x to the power of k, then if you remember the log rules, the logarithm rules, we can pull the k in front of the log and use the basic constant rule. We also have oftentimes, if we have the log of a function like log of u of x, we have to use the chain rule. So the derivative of log of u of x is u prime of x divided by u of x. And in general, for any positive base b, if we have, and we could kind of show that by changing the base of b to the power of x, we can show that the derivative of the derivative of b to the power of x is equal to log b times b to the power of x. All right. Lastly, another topic that we will encounter once we deal with functions that take multiple inputs is partial derivatives. So what happens when there is more than one variable that is changing. And ultimately, if you can do ordinary derivatives, you can also do partial derivatives. Ultimately, the way we deal with partial derivatives is to just hold all other input variables constant except for the one we're differentiating with respect to, right? So suppose we have a function f that is now a function of two or more variables like x and y, or x1 and x2, and we want to determine the rate of change relative to one of the variables. To do that, we basically just take the partial derivative and hold the other variable constant and only use one variable as kind of changing, and take the derivative with respect to that variable. Again, treating the other variable as if it was a constant. Okay, so we basically use the same function or the same definition of the derivative, where we now have a function with multiple inputs, and we're just looking at the rate of change if one of those x's, like in this case xi, is increased by h, and we use the same logic, increasing h, taking the limit for h approaching 0. We can also take higher order derivatives, like we did with the functions of a single variable, except for the fact that these higher order partial derivatives can be with respect to multiple variables. All right, so I'm gonna take a break here. In the next video, I will talk about integration.